looking at an example of momentum here. We're going to look at the impulse momentum theorem and just kind of momentum in general. So it'll kind of kill two birds with one stone here. So we have a 2,200 kilogram vehicle traveling 94 kilometers an hour, which is 26 meters per second. That can be stopped in 21 seconds by a gentle applying of the brakes. It can be stopped in 3.8 seconds if the driver slammed on the brake, or it can be 0.22 seconds if it hits a concrete wall. So what is the impulse exerted on the vehicle, the average force exerted on the vehicle in each of these stops? So we have three different scenarios. Scenario 1, which is the gentle braking, and then we have scenario 2, which is the hard braking, and then we have scenario 3, which is the wall. Okay, but this is going to give us some good practice with momentum and impulse. So in each of the scenarios we have an initial momentum we have to figure out. So it's going to be the same here. So remember, momentum is just moving mass. So momentum is signified by P, and that's mass times velocity. And then we can also have like an initial momentum, whatever we get for that, and then we'll have a final momentum after the object stops or when it crashes or something like that. If it is stopping or something like that, then this could be zero because momentum is mass times velocity. If your mass is not moving, your velocity is zero, then your final velocity would be zero here. Okay? So in each of these scenarios, we are stopping. So we're going to have a final momentum of 0, and since it's mass, moving mass, that's kilograms times meters per second for momentum, and that's going to be the same across the board here. And then we have an initial momentum, which is just going to be the mass of the vehicle, which is 2,200 kilograms, times its initial velocity that is moving. So at the initial velocity, we're going to use the meters per second, because everything needs to be in meters per second, because that's what we use for that label. Okay, so we're going to have 26 meters per second. So we get an initial momentum of 57,200 kilograms times meters per second. Now that's a pretty big number, but remember here we are working with a vehicle. We're working with a car. Okay, so this is our initial momentum there, and that is our final momentum. So in each of these three scenarios, the initial and final momentum are going to be the same because we're traveling that 26 meters per second and we're coming to a stop. What's going to change in each of these scenarios is the impulse. So impulse is going to be force over time. So the force of the impact over the time of the impact. So you can see in our scenarios we have three different times available. So that will allow us to calculate the force. So oftentimes impulse comes into play when you have vehicles crashing, vehicles stopping, two objects crashing with each other. We want to figure out the average force exerted in that time. Alright? So in general, the impulse is equally exerted on both objects, but what can change is that momentum, right? Because if we have consider we have a small object and a large object, the force between these two, the impulse between these two rather, would be the same if they crashed, but the change in momentum is going to be much greater for this one than it would be that one. So this one would have a little change in momentum, where this one would have a much larger change in momentum. Okay, so that's kind of the trade-off there. So forces and impulses are the same on two objects. Remember that. Okay, so looking back here, let's write our equation. So our impulse momentum theorem is force times delta t equals our change in momentum. Okay, and change in momentum is final momentum minus initial momentum. So we have our times for each one of these scenarios. Okay, so we're going to write that time down for each of our scenarios. That way we have something to plug in. So for scenario 1, it takes us 21 seconds to stop. For scenario 2, it takes us 3.8 seconds to stop. And scenario 3, it's going to take us 0.22 seconds to stop. So this is the one hitting the wall. So that's going to be a really quick stop, fairly quick stop, and a slower stop. Okay, So let's plug it into our equation that I have listed there below. Force times change in time. Usually change in time is 21, like it's just 21 seconds total for this one, however many seconds it takes us to stop. So 21 seconds is going to be change in momentum. So remember we said our final momentum, because we're coming to a stop, is going to be 0. So that would be 0 minus 57,200 kilograms times meters per second. So we can see that in general here, since we're coming to a stop, our force is going to be negative, which makes sense because we're slowing down, or there has to be a force pushing in the opposite direction in order to stop the object. Okay, so to solve this, 0 minus 57,200, that's just going to be that 57,200. So I'm not going to do anything there. I'm just going to divide by 21 seconds. And we get a force of negative 2,723.81. Okay, and that would be in newtons. So that is the force that we're going to get out of this. All right, now I kind of jumped ahead of myself a little bit here because the question that we had to ask here is, what is the impulse exerted on the vehicle? So remember, impulse, I'm kind of writing it out over here, impulse was F delta t. So the impulse here is going to be equal to the change in momentum. Well, the change in momentum is going to be the same for all three scenarios. It's going to be 0 minus 57,200. So that is just a negative 57,200. Okay? And this is usually given in Newton seconds. That's what the label for impulse is. Regardless, I know that, or we know that momentum is kilogram times meters per second. But when we're looking at impulse, we're looking at force times time. So a force times the time would be newtons for the force and seconds for the time. Okay, so this would be the answer to that first question. And that second question, we're going to go back to here and we're going to figure out the rest of these forces involved. Okay, so let's do this second one here. For the second one here, we'll have F delta t, and our delta t is 3.8 seconds. That's going to be equal to that negative 57,200 Newton seconds. All right, and then just like the last one, we would divide out the time, so divide by 3.8 on both sides, and we will get 260,000. So that should be a negative 260,000 newtons. And I also forgot the negative on this one. Since we're slowing down and we're coming to a stop, your force will be negative. Okay, so we can kind of analyze these three scenarios a little bit. We have a force of negative 2,723 here, negative 15,052 here, negative 260,000 here. The thing that changed here was the time. So if we look at how impulse works, if we have a longer time, then we're going to have a smaller force. Okay? So if we have a shorter time or a much smaller time, okay, then we're going to have a much larger force. So we can see we went from 21 seconds to 3.8 seconds, so that's quite a bit different. And our force went from 2,700 to 15,000. Okay? So a much smaller time equals a much larger force. So a scenario that goes with the first practice problem, we have a passenger of 85 kilogram mass in a vehicle described. For both gentle and hard braking situations, calculate the impulse and average force needed to bring the person to a stop along with the vehicle. Okay, so if we were looking at just the person here, let's say we're looking for the gentle and hard braking, so that would be scenario 1 and scenario 2. So the time for scenario 1 is 21 seconds. Time for scenario 2 is 3.8 seconds. So in this scenario, we're looking at just using the person. We're trying to figure out the momentum on the person here, the impulse on that person. So if we have our momentums here. Let's figure out our initial momentum here. So we are going 26 meters per second. So it's mass times velocity, which is 26 meters per second. Okay, so we're going to take that 85 times 26 meters per second, and we get 2,210. And that's kilograms times meters per second for our label. So that's our initial momentum. And in all scenarios here, again, our final momentum is going to be 0 because we are coming to a stop. Okay? So if we want to calculate the impulse, remember that's F delta T equals final minus initial momentum. Well, this is the impulse here. So really, we're just looking for delta P, or change in momentum, to get our impulse here. So it's going to be 0 minus 2,210 kilograms times meters per second. So our change is just negative 2210. And if we wanted to make that in labels of impulse, that is going to be Newton seconds. Okay, so that's going to be our impulse that we're going to be using. And now, so let's do this, F delta T. So our impulse equals that. Now we want to figure out our forces in scenario 1, which would be the gentle stopping, and scenario 2, which would be the more abrupt stopping. Okay, so we'll have F times our 21 seconds is going to be equal to negative 2210 Newton seconds for scenario 1. And scenario 2, we will have F times 3.8 seconds is equal to negative 2,210 Newton seconds. Okay? So we're going to divide these out here, and we will get our answer for both of them. Okay, so for scenario 1, we get a force of 105.24 newtons. Okay, so then for scenario 2, we get 581.58 newtons. Okay, so then we're going to ask ourselves here, analyze this a little bit. Does it make sense? Do I have a smaller time and a larger force? Yeah, so our time went down from 21 to 3.8, just like above, and our force went up. Okay, so a shorter time is going to equate to a larger force. Okay, so this would be our linear momentum. Let's check another problem. So now we have two cars traveling. We have a 770 kilogram car and a 1500 kilogram pickup truck. We got the car that's going 13 meters per second. So this is a collision scenario. Okay, the collision lasts 0.8 seconds, during which the impact force is 6,000 newtons. Okay, so what's the impulse in the scenario, and what's the final momentum for each vehicle? What is the final speed for each vehicle? Okay, so let's see what we can do here. Okay, so let's find our momentum for the car and then the momentum for the truck initially. Car here and truck here. Initial momentum for both of these. So for the car, we're going to have a 770 kilograms times 13 meters per second. And then the vehicle, or the truck, excuse me, the truck is 1,500 kilograms. And its speed is 8 meters per second. They're both going to the right here. Okay, so both velocities are going to the right for both of these. So they're going to hit each other, and then we're going to see what we get afterwards. So we don't know what the final momentum is for either one of these. But that's what we're going to find. So let's put initial momentum in our calculator, so we get for that. So initial momentum for these. So for the car we get 10,010. So 10,010 kilograms times meters per second. And for the truck we get 12,000 kilograms times meters per second. Okay, so now this one is worded a little bit differently than the last one. So it says, what is the impulse in the scenario? Well, remember, impulse is just force times change in time. And in the problem, or in this question here, we are given an average force of 6,000 newtons in this scenario, and then the time of the impact is 0.8 seconds. So we're given some information that we can just use to figure out our impulse. So A, the impulse, is just going to be, all right, F delta T, which is 6,000 newtons times 0.8 seconds, which is 4,800 newton seconds. All right, so now we have this, so that's the impulse, which is going to be the same on both of those. So remember I talked about that a little bit ago. The impulse is the same in a collision. Okay, so that car hits that truck, the impulse on that is going to be the same as the impulse on that. The thing that's going to change though is our final momentum. Okay, so momentum depends on the mass, so if you have a less massive object, then there's going to be a greater change of momentum than the much more massive object. Okay, so let's check it out. Let's see what we can get here. So we're going to use this for our impulse for both of these. Okay, so this will be your F delta T, which is just impulse, is 4,800 newton seconds for both of these. But we have to pay attention to the direction of the forces here. So the impulse on the car to the truck is going to be going that direction. Right? So the truck is going to have a positive impulse on it because something's hitting it from the back end, which matches up with the velocity here. Now the impulse on the car, so that's going to be from the truck, so that's going to be going that way because the truck is here hitting a force on the car, or an impulse on the car going back that way. So really the impulse on the car should be negative. Okay, so that's what's a little bit different in the scenario. So let's find the final momentums here with these impulses that we have. So for B, I have an impulse of negative 4,800 for the car, and that's newton seconds. Initial momentum is, we need final momentum here. Final momentum minus initial, so that's 10,010 kilograms times meters per second. So we're just going to add 10,010 to both sides. And that'll give us our final momentum. That will cancel out there. The units will give us kilograms times meters per second. So our final momentum of the car is 5,210 kilograms times meters per second. Okay, so the car slowed down after it hits the truck, which makes sense because the truck is more massive. So let's look at the final momentum of the truck here. So our impulse, 4,800 newton seconds. That's going to be equal to final momentum minus initial momentum, which is 12,000. Okay, so similarly, we're just going to add this value to both sides. Alright, so add 12,000. Alright, that'll take care of that. So we'll have 12,000 plus 4,800, which gives us a final momentum of the truck of 16,800 kilograms times meters per second. So that makes sense because the car is pushing on the truck. That would increase its momentum, which would increase its speed. So now the last piece here, we actually have to find the speed of both of these. Okay, so our car is 770 kilograms and the truck is 1,500 kilograms. Let's find our final speed. So we can break apart momentum. Remember, momentum is just mass times velocity. In this case, we're doing final velocity. And we just use the masses of each of the vehicles that were given. So we would have a 770 kilogram times final velocity equal to 5,210 kilograms meters per second. Okay, so let's set this next one up. So we have a 1,500 kilogram truck times this final velocity is equal to 16,800 kilograms times meters per second. So we just need to divide out these masses here to get what we want for our final velocity. Okay, so we'll divide by 1,500 here. So let's do that and see what we get for our final velocities. So for the car, we're going to have a final velocity of 6.77 meters per second. And for the truck, we're going to have a final velocity of 11.2 meters per second. Okay, so let's compare those to our original velocities. The car should be slower because its final velocity went down, and the truck should be faster because its final momentum went up. So we can see originally the car was going 13 meters per second, so that slowed down like we thought, and originally the truck was going 8 meters per second, which went to an increase to 11.2 meters per second. Okay? So here are a couple of linear momentum and impulse problems, and next we're going to be jumping to angular momentum and angular impulse. So in the second video, I'll be working through angular momentum and angular impulse, so please check that out if you want to look at those types of problems. Thank you.